So, Learning Malaysia, maybe on June. So, Tensorflow and Deep Learning Malaysia user group is actually a group that we allow people to come together and to create and learn about deep learning frameworks such as TensorFlow, PyTorch. At the same time, you also allow the in our group to actually build a skill set um, where they can learn about deep learning and machine learning from both the beginner, intermediate level, advancing to the advanced level. So the purpose of the group is actually for us to actually do knowledge sharing among ourselves. So today we are happy to have Dia, which is an ML research engineer intern at Ivy, to give a talk entitled KerasCV for the Young and Restless. So without further ado, I will pass the presentation over to you.
Hi. Good evening to the ones in Kuala Lumpur and everyone joining in virtually today. Kwan, could you please confirm if my screen is visible and everything's fine?
Yep. Yeah, it's visible.
Perfect. And my slides are perfect?
Yep.
Okay. All right, then I'll start. So again, good evening, everyone. My name is Swaditya Mukherjee, and I'm a ML for TensorFlow Core or Keras, and I'm also co-organizer for GDG Mag. Today's talk is around KerasCV for the young and restless, and we're going to be discussing how you can go from 0 to 1 for computer vision workflows development. So just a short, who am I? I'm a Google developer expert for ML TensorFlow Core. I'm an ML research engineer intern and a GSOC 23 org admin at Ivy. We are working towards unifying AI and solving problems between framework interoperability. So do check us out on the website. I'm also a research intern at the Center for Visual Information Technology at IIIT Hyderabad in India. I'm a co-organizer for GDG Bank. I have been a GDSC lead in 2021. I'm an ex-SD intern at Mosaic Wellness, and I'm a Barcelona supporter. So I love watching and enjoying the game of football. So yeah, without further ado, let's begin. Some notes before we start. Uh, Feel free to engage during the talk. Feel free to ask questions, raise your hand, and I'm sure we can just unmute. Doubts are dangerous, so let's have them solved as we go on. Don't keep them for the end. You can ask questions while we are in the session. I won't dive into too much math unless it is required to do so. So please feel free to grill me after the talk. Let's connect through LinkedIn, Instagram, Twitter, or any other such medium, and I'll be happy to answer any queries you have. Slides and associated demo code will be made available right after the session through QR code, and I shall share the slides and the links relevant to the session to Kwan, and I'm sure he can just send it across to you all. After the session is complete, feel free to ask any off-topic questions too, and we can have a good chat. So the things we're going to be covering today span through quite a few fields. We're going to be looking at what is computer vision and where Keras and KerasCV lie in the intersection of all these different concepts today. Yeah. So let's begin. Computer vision is just CNNs and deep learning. Well, that is something that would be said by a person trying to shoot themselves in the foot. That is not what computer vision is all about. Computer vision has a ton of different connotations. It has a ton of different tasks, such as image filtering, smoothing, blurring, any other solutions or problems that are being solved by computer vision aren't just being solved with CNNs, convolutional neural networks, or deep learning. There are traditional computer vision algorithms which do not have any kind of ML component in them, but they seem to do a very good job of what they are, accomplishing. So algorithmic methods exist. to do most of the tasks that we ask computer vision to do today. Like, for example, on the left, if you see an image of a noised, you see a noised image. You see something that you would see from probably a painting of a French village in probably the 1700s or 1800s. But you perform a very simple algorithm. You basically run a simple algorithm, which again does not have any kind of machine learning, and you can see something along the lines of the image on the right, where you have a much more cleaner and much more clearer image of what's happening, right? You don't need machine learning for every task in computer vision. Some of them are very well solved with more traditional methods, right? But then there are some tasks which don't get solved very easily with traditional algorithms. For example, what you see right here is a ton of different tasks happening together at the same time. They are object detection, they are segmentation, they are classification, and so on. And these are all different tasks that have been tried and tested for looking into from a side of the traditional algorithms, but they do not seem to work directly through traditional methods. So that's where deep learning had to come in. So moving forward, we look at how computer vision and deep learning came together, and we get the best of all worlds, quite literally. So you see, everything has a sort of confluence in the two fields. So computer vision and deep learning come together to find common solutions to larger problems to get the best of not just both, but all worlds at once. So now we're going to be looking at convolutions and how they are some of the most important, bedrocks for computer vision today. So what you see in a simple convolution is quite literally just a pixel-wise product and a summation with respect to a window, or sometimes what we also call as a kernel. These kernels are what present as sort of filters wherein you can interchangeably perform multiplication and summation, and these allow you to compress your image information very succinctly. What you can see on the right side of the GIF over there, you see that all of those numbers are being represented in smaller areas, which allow you to, again, as I mentioned, compress image information. Not only that, this is, if you can see carefully, this is a very parallelizable operation. You can parallelly perform the same operation across the entire image at the same time. And not only that, it is a very computationally efficient algorithm, simply because you can simply because it consists of multiplications and summations, something that is said to be, well, quite efficient in any architecture, RISC or anything of that sort. So just to drive in the idea a bit more, when it comes to 3D spaces, if you will, on the left, you'd see something like a 12 cross 10 image with 3 channels of R, G, and B. But on the right, you'd see a convolution layer, which has a bigger window size, right? What you're trying to do here is perform multiplication between the two purple boxes. These matrices, upon broadcasting and multiplication, will give a certain result, which is what we are looking to gather. This is how you would see a normal convolution layer working in production or in practice rather. So that's I hope this animation gives you some kind of intuition as to how you're working. So when you bring convolutions, the idea of just convolutions into neural networks, what if you change the windows, the kernels, from fixed numbers where you had them as certain values, like let's say 1 or 2 or 0 or -1 or something, and you make them learnable parameters. You make them a certain, you assign them a certain weight and bias, and you allow them to change with time through training with the virtue of backpropagation. You make the kernel learnable instead of leaving it fixed, and it learns to recognize features on its own. It learns to recognize edges or some certain shape or distinct feature, if you will. Now, when you have these features being detected by convolutional neural networks, you'd see something as you are currently seeing on your screen on the right. The GIF over here, for example, is taken from a convolutional neural network that broke the ImageNet challenge. So what you see here, all the different kinds of black and white pieces, these are the different things that a convolutional neural network layer is seeing. These this right here is an amalgamation of a ton of different CNN layer kernels being stitched together into one single frame. So when you get these edges, you get the distinct features, representations, and so on. You pass them into a vector space representation and you get a certain value. This vector space representation is representative of all the possible features in your image being extracted through the medium of such convolutional neural networks. To help drive in once again, what you see here is the features coming down into the dense representations by the virtue of the kernels or by the virtue of their learnable parameters, right? Each of those weights of 4, 4, and 3 are being compressed into dense representations and passed down. And that is again, drove in through a certain representation to give you a result in a feature space representation. So what you just saw is a convolutional neural network, how convolution works, and how it's supposed to perform some kind of transformation of an image to a certain vector space representation. Now we're going to be looking at attention and how that is all you're going to need. Now, I'm going to try and help build a simple intuition for you. So I'm going to ask you to involve yourself in a thought experiment of sorts. Imagine that you have 10 locks, 10 boxes, and 10 keys. And I have locked each box and taken the keys. Now, I am a very chaotic, evil person in real life. So I'm going to mix up all the keys and I'm going to tell you that, okay, look, you have a task. You have to open each key with each lock and give me the final result of which key is right for which lock. So at an individual level, I want you to take probably 30 seconds and think about how you would go about solving this problem, where you have 10 keys, 10 locks, and each of those locks, well, are put on the box, and your job is to open those boxes. So how would you go about them? Take probably 20-25 seconds. Well, I guess that's 15 to 20 seconds. So moving on. Uh, you'd look at a solution that would be something of this sort, where you have a brute force method. This brute force method is going to look like something where you try each key with each lock and it works, right? You have 10 cross 10 exactly. View the key pattern, see if it fits which lock. I mean, that's a good solution, I agree, but you can't really understand which key which would go with which lock just by seeing the key pattern, or can you? Unless you're a very proficient person with keys. I am not, so I can't help that. But on a very general level, what you're going to do and try is take a brute force approach where you're going to try each key with each lock. Now that is going to lead to 10 into 10 or 100 tries at a very bad level. Let's say your luck is very bad and you do not get the right key at every iteration, and you only get the right key after 10 tries. That's like a big complexity problem, right? So what would the solution possibly look like? Something on the right, where different keys match with different locks and they give certain results. That's what it would look like. Now, moving on, I want you to transfer this idea from locks, boxes, and keys to pixels of an image. Let's say the boxes are pixels of an image. So you have, let's say, a 28 cross 28 image. Take all the pixels of that image and consider them as individual boxes. I want you to consider them as individual locks and individual keys as well. Now run the same brute force experiment and try unlocking each of those boxes with each of those keys. What do you get? You're going to focus on the right lock key combination, correct? You're going to look at the ones similar to what I showed you on the last slide, where you're going to have a certain combination that does open a lock and a box, but some of them don't. The instance where you get the right lock with the right key, that is where you focus the most, correct? Each of those 10 instances in the last example for you is where your attention will lie. That is what you'd say attention is in a very simple and general term. Now, I know that neither is it this simple or is it this or is it mathematically sound, but I'm going to explain it a bit further with some math right in the next slide. But before that, if you can see the image right here, what you'll see is the heat map increases near the dog, and that is what an attention layer sees. When I say sees, I mean that each of those multiplications or each of those lock and key combinations seem to maximize at the same pixels where the dog is located. So the layer seems to very magically apply attention on those layers or on those pixels. So moving on, what you see right here is a simple neural self-attention mechanism. If you see right here, if you take a sentence called "the quick brown fox jumps over the lazy dash," can anyone complete the sentence? This is a very interesting sentence in the English alphabet. Drop it in the chat if you can. The quick brown fox jumps over the lazy dash. Well, the solution to that is dog. The quick brown fox jumps over the lazy dog. And this sentence is quite famous because it is one of the only sentences which utilizes each and every alphabet of the English language. So that's just like a fun bit of trivia in the middle of everything. Now, let's say that you take each and every word in there. The quick brown fox jumps over the lazy dash. The model currently is going to work towards predicting the word that would come in place of dash. So we are going to take each of those words. Let's take the example of the word quick. You take quick and you represent it in a certain embedding space. What is this embedding space? This embedding space is a certain vector representation where you're gonna transform the word quick to a certain vector. For the sake of simplicity, let's just consider them as numbers. Let's say you number them as 1, 2, 3, 4, 5, 6, 7, 8, and well, dash being 9. So you have different numbers. So quick would then result as a result be the number 1. Now imagine this number 1, but as a vector space representation. That is what you're gonna have as a embedding vector for the word quick. Now I want you to replicate this vector into three identical vectors. These three identical vectors are known as the query, the key, and the value, right? What we're now going to do is perform multiplication between query and key. Now, you're going to say that, well, if I multiply the same thing together, shouldn't it just be the square? You're right, it should be. But we're also going to be performing the multiplication across the entire sentence. So we're going to take the query of quick and we're going to take the key of, let's say, the word jumps. We're going to perform multiplication between the embedding representations of those words as well. Along similar lines, we'd also pick up the word, the query of, let's say, the word brown and the word fox. And we're going to perform multiplication over that as well, such that you would get a matrix of, well, for here, 8 cross 8, where each of those represent, or each of those values is a multiplication between each and every embedding representation that you have between the queries and the keys. Once you have the queries and the keys together, what you're going to do is perform a softmax operation on the last dimension. What the softmax operation is going to do is give you the result. It's going to balance the probability distribution such that you can find out what is the highest value, what is the lowest value, and get you a uniform method of seeing everything in a certain range. Finally, what you're going to do with this certain range is multiply it with the value, or the value being the third vector that you had identically created. Once you have done this multiplication as well as the value multiplication, you're going to pass it through a dense layer. This dense layer is our simple friendly neighborhood dense layer, which you can define as like a perceptron, and that will give you a resultant output. This resultant output is a certain representation of two dimensions, and this will help you to, well, gauge what kind of attention has been applied. That is the result of your attention mechanism, and that for you is a very simple, or rather generic introduction to attention as a mechanism. Once you do that across a certain set of images, what you'd see is something as you see on the screen now. Over here, you see that the dinosaur is moving and the attention layer is performing attention on the dinosaur, the tail, the moving human, and everything in there, right? That's the kind of attention that a layer of that sort would provide. Now, I'm sure that folks who also focus on explainability can appreciate the fact that it is a very explainable mechanism where each and every decision that is being made is very well represented through these visuals right here. So what you just saw was a very brief introduction to convolutions and attentions. And now we'll just dive into a very short introduction to Keras. Accelerating ML with Keras. So Keras was developed by Francois Chollet in 2015, and it was started as an internal research project within Google. Keras was a higher level API that was built on top of different backends like TensorFlow, Theano, Cafe, etc. And it was available for folks to use as and when they require it. It had a default TensorFlow backend, and it was supposed to be fully free and open source. It currently is. So some features in Keras and why you should consider it as your first and last ML framework. Well, first off, it has a large community built from the ground up by folks at Google, by folks across the world through the open source framework. It has grown to large heights and it is only growing further. Strong documentation support. Keras is one of the most well-documented pieces of software on the internet. The community is very welcoming and you can learn advanced computer vision, machine learning, natural language processing, generative AI, and different kinds of concepts and how they work with Keras directly through the documentation itself. It is production ready. It is made for full compatibility within the TFX ecosystem or the TensorFlow extended ecosystem, which makes sure that you can use Keras models with TFJS, TF-Lite, TensorFlow serving, TensorFlow datasets, and much more. Finally, it is extensible. You can implement your own activations, your own layers, your own models, and your own designs within Keras at once. You do not need to rebuild the wheel for what already exists, but you have the choice of extending already existing layers or other modules. So that was just a very quick introduction to Keras and what Keras can do. Now let's take a look at KerasCV, which is why we're here. So KerasCV for the young or for the ones who are just beginning with computer vision. Well, KerasCV is a library of vision-oriented Keras components, and it supports a ton of great features like mixed precision, XLA compilation, TPUs, and more right out of the box. It does not require help aside. It can do so directly. There are vision tools for everything, and you can use them extensively. It can be for industry grade deployments, which require you to deploy across multiple clusters of GPUs. It can be tech for onboard GPUs, like something on a Raspberry Pi or a drone or a mobile phone or edge devices, any of those. Keras will help you to design for those devices. Lastly, get pre-trained components with out-of-the-box support, because as individual developers, it's hard to train large-scale models, like maybe something with 10 billion parameters or so on. It costs too much for an individual. So there is already pre-trained components available that you can directly drop in and work with. For the restless ones who are eager to start building right away, there is support for models like Stable Diffusion, YOLO, CSP Darknet, EfficientNet, and major computer vision models rightly available already. Other vision tasks are now first-class citizens with full support for bounding boxes and segmentation map utilities. You do not need to think about how you're going to integrate niche computer vision tasks like image segmentation or object detection, because now those are fully supported directly within KerasCV. There is a very modular API to mix and match components, because the API aligns with Keras NLP, which is a sister library for KerasCV with NLP components. You can mix and match for making your own kind of model. Lastly, there are extensive guides and examples that are available to start you on your journey. So that was KerasCV. Now, I want to talk about what KerasCV can actually do. Imagine KerasCV for image augmentation. You have the latest layers like augmix, cutmix, Fourier mix, and much more. If you're confused, use rand augment. It will allow you to randomly choose augmentation layers and perform augmentations which vary in themselves, which just help make your model much more robust to change. Not only that, it also has support for bounding boxes, so that you do not need to worry about how you're going to handle the labels as well. KerasCV for object detection. Now, with all the different objects in a frame, it becomes difficult to directly start working. So now KerasCV provides full support for YOLO V8 and RetinaNet, and a few other object detection models are on the way. 2D and 3D modalities both are supported out of the box. So what you see on the screen is 2D, but let's say you had depth as well. You could also design 3D bounding boxes, which would allow you to, well, expand more information out at the same time. KerasCV for image segmentation. Rapid development is in progress towards adding segmentation models. Their utilities already exist, but we are currently in the process of adding more. Visualization APIs for segmentation models are already present, and it helps you to get more information about the kind of data that you have right out of the box. Lastly, something that has been doing the rounds nowadays on the internet. Let your imagination run wild with KerasCV, because you have support for pre-trained models like Stable Diffusion, version 1 and version 2. You have elaborate documentation on how to play with it, and you can extend Stable Diffusion with textual inversion, Dream Booth, or you could even look towards implementing your own DDPMs or DDIMs with KerasCV. So what you just saw was a brief idea about what KerasCV is and a sneak peek towards what KerasCV looks like and what it can do. Now we're gonna take KerasCV for a spin. Now it's time to get your hands dirty, or at least watch me do it. What we're going to be doing today is generating high fidelity images with stable diffusion, because I'm pretty sure that you just don't want to see some boxes around images, right? You want to make your own images. So let's dive right in. Can someone confirm if my screen is completely visible yet? Perfect. Perfect. So let me share this link. Feel free to make a copy of this. I'm going to be running it right now. So feel free to make a copy and run, but I'll do the needful right away. Where now what we're going to see is a comparative study between stable diffusion of different types. What we're going to be looking at is a certain version of stable diffusion in general as a raw model. We're going to be looking at stable diffusion with XLA compilation. We're going to be looking at stable diffusion with mixed precision. And finally, we're going to be looking at stable diffusion with mixed precision and XLA compilation. We're going to compare the timings for inference between all of those models and see what kind of imaginative images it can give us. So setting everything up, let's just dive right in. While all of this happens, I'm very happy to field any questions that you all drop in the chat. Okay. So now we're just going to look at stable diffusion. So once you import from KerasCV, it's a direct three-liner model. So KerasCV import stable diffusion. You're going to take the raw model. So the API key is not necessary right now, but you can use weights and biases. That's what I'm using currently. I'll drop a link to weights and biases as well in there. So this API key is just, I mean, it's good to have probably, but so weights and biases is a platform which allows you to, well, get metrics and track all your experiments at once. So that's what I'm using currently. Weights and biases is also called WantB in short. So you can use WantB to track all your experiments in a very neat manner. So I'm gonna take a look here. Okay, so does anyone want to suggest any stable diffusion prompts? Some interesting prompt. For example, right now we have Wolverine trying to pick a lock with his claws, but I'm open to any other prompt that anyone would like to try out. Let's have something interesting or imaginative. Nothing too easy for the model. Anyone? Feel free to drop it in the chat if you do. Petronas twin towers in a fungus infected world. That's a very interesting prompt. Let me try that out. Not too sure if he'll know what the Petronas twin towers are, but I mean, one can hope, I guess. Okay, so let's just run this experiment first. Won't.init. If you want to try without weights and biases, you can just comment out any line which starts with won't be. So you can just comment these out and you'll get everything that you want right here. So what has started right now is the downloading of the models from the internet. It's going to download the VAE, it's going to download the text encoders, it's going to download everything that it needs to set up the pre-trained model for you. The images that we're going to generate it are of the size 512 cross 512. So these are pretty big images. These aren't small. So let's just take a look at what comes out of it. So now what you're going to see is the model trying to generate images. It's going to take 1 minute and 35 seconds to generate 3 images of that size for the given prompt. So just let's check it out. Let's see where it takes us. Once again, if anyone has any questions, any comments, any doubts, please feel free to put them in the chat and we can have a quick discussion while the generations happen. Okay, so it seems that our generation is complete. And now what we're going to look at, I want to ask, what does the stable diffusion mean? We're trying to generate an image now. Yes. So now I'm sure that most of us have come across ChatGPT, where you put some text information and you get some text information as a result, right? Now imagine that you put some text information and you get a complete image out of it. That is what stable diffusion enables, and this is completely open source. So that's what we're going to look at, how KerasCV is enabling stable diffusion. I hope that answers your question. Yeah, so it seems that our run is complete. So let's look at the uh, images. Well, that's the kind of images we get, and I'm pretty sure Petronas Twintas aren't three twins, or that they don't have two bridges between them. But yeah, it seems that's the model things. This one looks interesting. Well, not sure how the fungus part plays in, but yeah. And this one too. This is quite interesting as well. Fungus, no fungus infection. I agree. This is a very. It seems the model is confused. So fungus isn't something it learns well. Let's see. Uh, Now what we're going to look at is mixed precision. What is mixed precision? It will allow your model to compress tensors which are normally of size float 32 or the type float 32 to float 16. What this does is decrease your model size. This allows you to shorten the file and make the it just shortens your entire processing time and cuts down on resource usage at the same time. And this can prove to be a very good resource for performing training on a very limited compute requirement. So now we're going to look at setting mixed precision. It is done using keras.mixedprecision.set global policy. Now we're also going to do something called warming up the model. What warming up really does is basically just allows the model to execute once, and this execution will allow the model to trace the entire model graph. Tracing it will allow us a shorter inference time afterwards. So what you saw here for a minute, and so what you saw here, the generation time took 287 seconds. Now this time we're going to make sure that it's far lower. So now I've started it. It does have the files, so it won't download them, but now we're going to see it working together. Oh my, the prompt is Wolverine trying to pick a lock with his claws this time. I hope that's fine. Let's try different prompts for different models. So this time we're having Wolverine trying to pick a lock with his claws. We have two more examples. So if anyone wants to put two more prompts, just drop them in the chat. We'll try them out in the next two experiments. Superman and Batgirl riding a bicycle on a beach with a beautiful sunset at the background. That is very imaginative. Let's try that. Let's see where that takes us. I'm kind of curious myself as to what will happen on this one. So what you see is now the model is warming up. This is a warming up step that is going to help it trace the graph and let it understand what kind of functions are there, and so it will be able to execute quicker on the next run. How nice if the image generation could be set up. Exactly. Now that's what we're going to be looking at. What you saw in the first time was a very slow model, and that was without any kind of optimization. That's what we are going to do in our next experiments, increase the speed of the model. For the first time, it takes some time to trace it and perform everything, but after it'll be far quicker than what you saw in the first example. And we're going to see some graphs as well around it and why it's so quicker. So now after the warming up step, now it's going to generate on the basis of this prompt, Wolverine trying to pick a lock with his claws. Let's see what happens. Now look at this. What took 1 minute and 20 seconds or 1 minute and 30 seconds is far quicker here. There you go. Generation is complete. And we have some images right here. Going back, let's check what happened this time. So if you want to speed up the process, you can look at getting better compute, like probably an A100 GPU or V100 or something of that sort. That should help you increase the speed. Let's see what oh my, look at that. That's Wolverine and claws, but I don't see a lock. This is interesting. You see some kind of a lock mechanism, but you don't see uh, some kind of result. And then you have a bald Wolverine. Not sure if I've seen that one, but yeah, I mean that's 3 results. But if you were to look at the generation time, which is what I want to focus on now, you're going to see a drastic change. You're going to see that the difference in time is just that much. With mixed precision, what took 287 seconds to generate just took 65 seconds with a simple turn of a switch. That's it. One single line of code changing this line brings us to that big of a performance boost. So that's what I want to show you. Now, what if you perform XLA compilation? XLA compilation allows you to compile your model and perform a sort of kernel development, which allows you to create optimized kernels specific to your model. This is done with something called the XLA compiler or the accelerated linear algebra compiler, which is meant for optimized operations on any kind of architecture or like computer hardware. So XLA will allow you to speed up your process far more than what we just saw. But not as much as mixed precision for stable diffusion specifically, because in stable diffusion, the impact of mixed precision allows you to reduce the model size drastically, thus leading you to have a smaller model footprint as well. So now we're gonna look at what this will produce just with XLA, but having the traditional precision of float 32 instead of float 16. In the meanwhile, we have one last space for a prompt. So if you want to try out a prompt and see how it performs, uh, put it in the chat. To perform XLA compilation, all you need to do is pass this argument, JIT compile equal to true. That's all you need to do. And it will perform the required XLA compilation on your backend. Oh, by the way, it seems I need to restart the runtime because in my earlier experiments, I saw that it doesn't seem to handle more than two models at the same time. So I'll just restart the runtime and check. Aha, won't be knows who I am. Perfect. Okay. Uh, there we go. Yeah. Yeah, right there. So the resource exhausted error will come because have you tried shifting to a GPU runtime? Because you need GPUs for this experiment. You can do so with clicking on runtime and moving into change runtime type. Yeah, that should allow you to get a GPU notebook and you can execute with that. So XLA normally takes a longer time because it's compiling the model completely, but generation time improves drastically. So it's worth the wait for the first time. So in the meanwhile, again, if anyone has any questions, thoughts, comments, please feel free to just post them in the chat. So now the model is warming up and we are seeing that step happening. Okay, so the warm up is complete. And now we're going to be looking at the actual generation of the model. It's going to take another minute or so, but it's going to be quicker than the first raw model with no kind of optimization. How do you determine XLA and mixed precision as the manipulated variable to increase speed performance of KerasCV stable diffusion? I'm not sure what your question means, but if you're asking as to why they do so, so mixed precision just reduces the size of your model. It reduces the number of calculations required within the model. So mixed precision is just reducing the precision of your model and reducing the number of calculations. So it just inherently speeds up your model with lesser number of operations to do. XLA, on the other hand, just makes your model more compliant with the architecture and uses a C++ runtime or C runtime underneath it, such that it's able to harness the hardware on a much more granular level than Python would, which just ends up being far more quicker because Python and more native languages like C, C++ have a significant difference in speed of execution. So that is pretty much the reasoning. Now, what you saw up here, for example, over here you can see that with no XLA and no mixed precision, the time taken was around 287 seconds. But with mixed precision but no XLA, it took just 65 seconds, right? That's the kind of difference that these small optimizations can make. The flip side of performing the mixed precision is that it reduces the model's precision, or it reduces the number of bits per tensor that is present within your model, thus allowing it to be a bit less expressive. But it isn't a major cause for concern because in terms of stable diffusion specifically, it is not a drastic change. It's a minimal change. I hope that answers your question as best as I can. Yeah. So just to give a walkthrough of what each cell is doing, on a general note, it's initiating a run on wandb. It's setting a config variable. It just tells wandb to log these two values of the image height and image width. We are defining the stable diffusion model here, which just requires you to put the image height, the image width, and if you're doing XLA compilation, setting JIT compile to true. You're going to warm up the model and try to trace the graph for the model. Finally, you're going to perform a time calculation. In between it, you're going to execute your prompt, wherein you're going to run the text to image function on the model, pass your text prompt and the number of images you wanted to generate. Then you're going to pass and create a list of all these images that are being generated and pass them into wandb, and you're going to log them. Finally, you're just clearing up all the models. You're resetting the default graph and clearing the backend session to release all the GPU memory. Lastly, you're finishing the wandb run such that it gets completely logged. So now you can see that it took 110 seconds for the model to generate the next run, which is more than what it took for mixed precision alone. But this time you had no mixed precision, you had only XLA, and it took 110 seconds, which is far more efficient than what the original no optimization stable diffusion gave. So this is what it looks like. That's a very good scene, of course. Uh, so if we just take a look at the latest examples of the run, you would see that this is one. Interesting. Superman seems to have a very weird face in there. This looks nicer, but I don't see a cycle. So that's another problem. Uh, for the prompt, riding a bicycle on the beach with a beautiful sunset. It seems to fulfill some of the problems. It doesn't fulfill all of the problems. This one, for example, seems to have them flying on top of water. But yeah, I mean, fair enough. And lastly, what we're going to do is combine both the optimizations. We saw mixed precision and we saw XLA. Now, what if we combine both of them? That's what we're going to do here. Now, lastly, I take the liberty of putting a prompt myself, or if someone wants to still give a prompt, I'm more than happy to put that. Uh, let's try something. Was there anything there? Nope. So maybe we'll put something of the sort of hmm, let's try cat running behind a dog on a beach with a night sky and shining sea water. I don't know. Let's see what happens. Let's make it a bit more fun. Instead of cat, let's do a cheetah running behind a dog. Let's make it a bit more hilarious. Okay, so we have XLA and mixed precision running this time. Let's see what happens. So now the warm up has started, and it takes significantly lesser time now because XLA and mixed precision have taken over. So let's see what that means for our prompt generation time as well. The warm up is complete, and now we are going to see the actual generation time for the prompt that we had provided it. Cheetah running behind a dog on a beach, the night sky and shining seawater. There you go. With with those models giving over a minute, this is just taking 30 seconds. So that's the kind of speed up we're looking at. Now, there you go. That's it. Perfect. So now that I go into Wandby, I can just take a look at the kind of runs that took place. Uh, so what was the generation? Huh, that's not a dog. That is close, but I don't see a dog in there. That's a very good looking cheetah and somewhat of a night sky with a good-ish shadow, but no dog again. That's interesting. It didn't seem to catch a dog, but well, yeah, I guess. So aside from what the image generation, what I want to highlight is this right here. What you see is the original model taking 287 seconds to generate just 3 images. On the other hand, with mixed precision but no XLA, it took 65 seconds. With XLA but no mixed precision, it took 110 seconds. But with XLA and mixed precision, it took 32 seconds. This is the kind of difference that can be made with small optimizations, which just amount to like maybe 1 or 2 lines of code. So that's what the demo was about. And lastly, coming back to the slides, what you saw was the generation of stable diffusion images. Now, finally, we're going to take a trip around the resources. You're not a Vision Pro already. There are a lot of things to explore in computer vision. So if you're a beginner, look at the Keras.io examples. PyImage Search is a great resource for starting out. Also, look at Towards Data Science as a great resource for blogs that cover wide-ranging topics for computer vision. If you're restless and you want to begin with computer vision and building around it, look at some great videos from the First Principles of Computer Vision, which is a course by Columbia University. It covers some very interesting and important basics for computer vision. Also look at KerasCV documentation. It includes a ton of great details and nuances or ideas about how you can build around KerasCV. Lastly, if you want to expand beyond KerasCV as well, look at Hugging Face and their computer vision tasks available, which help you to get a head start on what you're trying to build. So yeah, I guess that's all the different kinds of things that we've been looking at. And we've covered all of these topics till now. So lastly, thank you, or terima kasih.
Thank
Yeah.
you. So yeah, I think this enlightening. Anyone have any questions you want to ask in the chat?
I'm more than happy to answer any questions that anyone would have. And about the slides, please find the link over here. There you go. I hope that link works.
Yep.
Oh no, it doesn't. It seems. One sec. Let me just check my Bitly and tell you what the right link is. Yeah, about the question, what are the alternatives to KerasCV in building stable diffusion? I'll just stop sharing if that's fine. So what are the alternatives to, wait, where's the chat? There you go. To KerasCV in building stable diffusion, you can look at Hugging Face. Hugging Face is a great way to start. There's the diffusers library from Hugging Face, which also allows you to explore other stable diffusion models like, let's say, textual inversion, dream booth, and much more. So feel free to look into Hugging Face. Otherwise, you also have PyTorch, but PyTorch is a bit more difficult to work with in the beginning. You may have some problems, so you can look aside from that. But in TensorFlow specifically, you can look at this. Uh, one sec. Oh, it seems I'd never created the link in the first place. That's very interesting. Apologies. So
I should give you your slides.
yes. Yeah, that. But if someone just wants to have a shorter link of some sort, so they can take that.
You're looking though.
Yeah. Yes. There you go. So yeah, there's a shorter link which looks more easier to remember. So you can take a look at that. Also,
I know why your previous QR code is for Calcutta.
yeah. So I gave a similar talk in Calcutta, and they had that was offline though, and that was so yeah, the slides are here, so you can take a quick look. It's practically it's practically identical except for a few small changes here and there in the experiments. So yeah, I guess that's pretty much it. Yeah.
Okay. Thank you, for the fruitful, insightful talk. So for the rest of the members that attended, so this is recorded. We'll upload the link to the slides and also the Google Colab together into our Facebook page. Our post page one is actually uploaded to the YouTube channel. Very much. Go.
I can't seem to hear you.
Uh,
One second. Could you probably try changing your mic or something, or something of that sort, some settings?
Yeah, can you hear me now?
Yeah, perfect.
Yeah. Good.
I again couldn't hear a large part of what you were saying.
Yeah, too bad. Yeah, so thank you very much.
I can't hear you clearly again. Yeah, folks on the chat as well. Maybe try a generic mic off. No idea.
Can you hear me now?
Yeah.
I think there's something wrong with the Bluetooth speaker.
So
I'm saying that hopefully next week at Bangalore.
Yeah.
Well,
yeah.
And for the rest of the participants, the event is recorded, and then we will upload together with the link to the slides and the Google Colab and the video into our YouTube page. Okay.
Yep.
Okay. Thank you very much.
All right. Thank you. Bye bye. Have a great day ahead.